All right, can everyone hear me okay? First, thanks everyone for being here. I'm excited to talk about one of my favorite topics, Neuroevolution, and Darwin, a C++ Neuroevolution framework. The slide deck has 3 halves, and I'll try to go through evolutionary algorithms, a quick overview of the Darwin framework, and finish with some notes on the technical implementation notes. So what exactly are evolutionary algorithms? Does genetic algorithms or genetic programming sound familiar? I forgot to ask, is anyone familiar with neuroevolution here? All right, awesome. So all of these are types of evolutionary algorithms which are nature-inspired algorithms loosely based on the mechanics of biological evolution, selection, reproduction, mutation, and they are optimization algorithms, meaning that they attempt to find the best out of many potential solutions to a problem. Before diving any deeper, I'd like to show you a couple of videos to give you a taste. Go ahead.
Where does mutation fit into your circle there?
It's part of the reproduction. So reproduction, I put here as a general thing for crossover and mutation. I'm gonna go a bit more into the details. But yes, that's a good question. The reproduction here is like a placeholder for everything that happens in creating new solutions. So hopefully this is going to work. It's running to my phone.
I think if you mash L on the keyboard.
Oh. So L?
Yeah. No?
All right. Let me give it another time here. And let me give it here. That's something I didn't quite expect. I'll try this again here. Let's see if I can move. This is a kind of video now to use all the time. Nice to meet you. So.
And also just open the YouTube video in a separate tab and then go back to the slides.
Okay, so this is actually the part that I wanted to show you. It's the first bit. Just a small for you.
So what is it using for feedback for positive score?
This one is the distance, I believe. Is the distance travel. That is the question.
Well, I mean, for each motion, it doesn't have a particular feedback that was good, just that it managed to get so many steps.
I have a link to that video, which is part of a research paper, so I can share that with you. It's not my project, so I don't want to go too deep into that. But we can chat about this after the talk. So, what do you think? I hope you are at least a bit intrigued. Now, despite being able to tackle very complex problem spaces, evolutionary algorithms have a very simple structure. And this is it. The blue part is what defines the problem. And the green parts are the ingredients of the specific type of evolutionary algorithm that we use. And I'm gonna go back to this, and I will show you how this translates concretely into C++ code in the Darwin Framework. Any questions so far? Yes?
So the crossover there means, sexual reproduction as opposed to asexual reproduction?
Correct. And I'll get to that in a bit.
Okay.
And actually, I'll get there very soon. So let's start with a very simple example. The traveling salesman problem. And the problem is given a set of cities. Try to find a route which visits every city exactly once and goes back to the original city. And we want to find a route that has the smallest total length. And we're going to try to solve this using genetic programming. And genetic programming, like all the evolutionary algorithms, it's a population-based search. So we're going to deal with a set of potential solutions, which means that we have to have a way of encoding a solution. So that's the first ingredient that we need. So let's say we have this route. A natural and simple, although not the only way, to encode a solution is to simply list all the cities in the order they appear in the route. Right? So one in the left, CB, CBD, A, and he wraps around. Does it make sense so far? And the next part, and this is going to get straight to the crossover thing, is how do we combine, having two solutions, how do we combine them into one solution? And this is the crossover operator. This is one example of the crossover operator which is specific to this problem and specific to this encoding. But in general, crossover is what was pointed out is sexual reproduction. We have two parents producing one offspring. So this particular crossover operation, I believe it's called OX crossover for the TSP problem, simply picks a random substring in parent 1 and it copies directly to the offspring, BD, and then it fills the rest of the cities with the cities from 1 to preserving the order. So, and then the next operator is mutation. Mutation here is taking two random cities in a solution and swapping them. So we get something like this. Now putting everything together, we are going to start with a population, let's say 100 random routes. And then for each route, we are going to calculate the total route length. And we'll use that as a fitness value for that particular solution. Then we rank all the solutions by fitness, and we keep the top half and we discard the bottom half. And with the half that we kept, we are going to pick up pairs of parents, random pairs of parents, and apply the crossover and the mutation struct here until we generate a new generation, another set of 100 solutions. And we had a repeat. That's pretty much the whole loop in the evolutionary algorithm structure. And we keep doing this until we either find a acceptable solution. Let's say we have a threshold and we find a route that's under that threshold, or we can limit by the number of generations. We can run it for, let's say, 1,000 generations, or many other stopping criteria. So we can have a predetermined amount of time that we let the algorithm run, or we can look at the convergence and stop if the algorithm doesn't make progress, or many other things that we can do. Any questions so far? All right, so since evolution algorithms are optimization algorithms, they can be used for any optimization problem. My particular interests are the last two, robotics and artificial life and AI. But not only, like the biggest problem has nothing to do with AI, it's just a pure optimization problem. And this is the second important concept I want to introduce here. Is anyone familiar with artificial neural networks? Awesome. So the basic ingredient for artificial neural networks is the artificial neuron. And it looks something like this. It has inputs, and for each input it has an associated weight. And the first thing it does is a weighted sum of the inputs. It passes that weighted sum to an activation function, and the result is the output value from the artificial neuron. And if we put together a set of these artificial neurons, we get an artificial neural network. The first example here is a very regular, very neat topology. It's organized in layers. The green circles are the input values. We have some hidden neurons in the middle, and then the output values. This is called a feed-forward neural network. It's a fully connected feed-forward neural network. So feed-forward means simply that the information passes from left to right. Yes?
Is the way that somehow actual neurons work, or is that just kind of an invention or supposition of how neurons work?
It's a very loose approximation, right? The same thing as the evolution algorithms are loosely inspired by natural evolution. They're not, perfect reproductions of the biological mechanisms. The artificial neural networks are also like a very loose approximation. This is actually a very extreme approximation, very simplified. So it's a very distant approximation. It's very far. Like there are a lot of different things that are different between the biological neurons and neural networks. But it's a useful approximation. That's why we start with this. This is also one of the simple models for putting neurons together. So feed-forward has the information left to right, and fully connected means that each neuron is connected to all the neurons in the previous layer, but they're not connected within the same layer. Any other questions? Okay, so we have another example of a neural network. It's a bit more, we got to be more creative here. It doesn't have layers. It still has, hidden neurons. So hidden neurons is anything that's not going to know, right? But it has a new type of connection. The red one goes back, and it forms a cycle. And this has a very important consequence. It makes the neural network a lot more powerful than the previous one. It is the basic ingredient for having some form of state in the neural network. This one, you can have as many neurons and as many layers you want. It doesn't have any state. It's a simple function. You have a set of inputs, it's going to produce exactly the same output. It's a pure function. So it limits a lot of the things you can do. Once we have the second type, which is called the recurrent neural network, it opens new possibilities. Just a bit of context here. I'm not going to talk about machine learning or AI. If you guys have any questions, I'll be more than happy to try to answer them. But I want to just define a bit the scale that we're looking at. So, somewhere close to the intersection between ML and AI, we have something called deep learning. Deep learning is training artificial neural networks using machine learning. And using a specific type of machine learning, usually for back propagation and gradient descent. Now, this is the point where we can introduce neuroevolution. So neuroevolution is simply the idea of using evolutionary algorithms to train neural networks. So if you go back to the previous picture and if we add evolutionary algorithms here, neuroevolution is kind of there. So it's similar to deep learning in a way that, in a sense, it also deals with training artificial neural networks. But it trains it through evolutionary algorithms instead of using back propagation. So this is the second part of the talk. If you guys have any questions about the concepts that we just introduced?
So how do you determine the weights in order to get that special loop and special?
That's a good question, right? So, you can think of the neural network as a black box. It has some inputs and some outputs. And the question is, how do you define what's inside, right? There are many things that define what's inside. One of them is the topology, like how things are connected. Then there is the type of the neural network itself. Like I showed you one type of artificial neural network, which is the simplest one, but it's not the only one. There are other things, like you've probably heard of LSTM, which are more sophisticated type of cells that using neural networks. So you can vary the type of neural network, you can vary how things are connected, and then you can vary the connection weights themselves. The connection weights are referred to as parameters of the neural network. Everything else is considered to be, is called hyperparameters. Now, certain algorithms only train parameters, only train the weights. There are other classes of algorithms which can train just the topology, just the hyperparameters. And then there are algorithms which can train both. Neuroevolution is interesting because it has the ability of training both, and I'll mention that. How exactly it does? There are a lot of details. I won't be able to cover everything, but it goes back to the concepts that I introduced earlier. The encoding of the solution. How do you encode a neural network? And then what kind of crossover mutation you do? So the simplest case is conventional neuroevolution, where you just train the weights, and then the encoding of the solution is just an array of weights. And the crossover can be as simple as like taking, like maybe half of the weights from one parent, half from the other. Right? Mutation meaning maybe like small tweaks to the weights. If you're talking about like changing the topology, changing the connections, then you have to encode the connection. Essentially, it's a graph, and there are many different ways. If we have time, I will mention some of these things, but I would like to introduce all the concepts before going to that level of detail. Does that make sense?
Sounds good.
So, first of all, I didn't set out with the goal of creating a framework. That'd be insane. Starting with just creating a framework. So, I was doing a lot of on-off experiments, neuroevolution experiments, and one of the nice things about neuroevolution and evolutionary algorithms in general is that it's really easy to get something put together. The loop is very simple. You can easily hack some crossover or mutational creators together and get something interesting. But after you do this for maybe half a dozen times it gets really old. Like a lot of stuff becomes very repetitive. So the first motivation was I want to do more of the fun stuff, which is creating new experiments and not reimplement the same thing again and again. The second reason is I'm going to domains and the problems. Like in the framework, I refer to the problem space as domains, and the specific algorithms are algorithms or populations. So if you have a one-off experiment, usually you craft like an algorithm and you craft a domain, you put them together, and you have a standalone program that you run, and it's really cool. But if I have, n domains, n problems, and m algorithms, I would like to be able to like try different combinations, not like hard code every single one, right? So another motivation in the framework is I want to reduce like the matrix of n times n to n plus m. It's kind of like a compiler. You have like the back end and the front end, like the source language and the target language. The third reason for creating the framework was that I want to do a bit more structured experimentation, and this is really important because you can get something that looks really cool, but if you do small variations, you try different things. Some things may work, some things may not. It's really hard to keep track of what worked, what didn't work, going back to the things that you tried, or putting things in perspective or comparing variations. So the idea is I want to be able to track all the variations of each experiment. I want to track the results. I want to have ways to visualize and introspect what happened. And finally, the last thing is when you do like small one-off experiments, it's really hard to justify building something super sophisticated. Even something like plotting fitness, you're not going to spend a week building a really nice fitness graph or an experiment that you did in half a day. So with the framework, it's easier to justify building some of these things because you're going to reuse them. You're going to amortize over multiple experiments. So just a quick rehash of the key concepts here. So we talked about the solution encoding and borrowing from biology. We are going to use the term genotype. Then there is the solution materialization, the phenotype. We have a population, and then we have the fitness evaluation, which is part of the domain. And I'm going to show you how these things map into the Darwin domain. This captures the key interfaces in the framework. There is a lot of machinery around it, but it boils down to these interfaces. If you want to build a new domain, and the domain can be something like the traveling salesman problem, or it can be some robotics thing. You have to implement the domain. And what a domain does is simply evaluating a population. That's its job. It's intentionally very generic. You have a population and you evaluate. You assign fitness values. That's what the domain does. You can do it by, measuring a route length, or it can be running a simulation to see how well a robot does in an environment. But ultimately, the domain is assigning the fitness to each individual in the population. And the population is a container for genotypes. It's a set of genotypes, like the solution encodings. And genotypes are the seeds for creating the materialized solutions, the brains. So a genotype is the encoding, and the brain is the thing that can actually set inputs, let it evaluate the output values. So this is the version of the earlier pseudocode that I showed. This is how things look in the Darwin framework. There's more machinery around it, but The gist is exactly this. Again, color-coded similarity. Population is green, domain is blue. Does it make sense? So, now this is one of the pieces of machinery that is not really part of creating the full experiments, but it goes back to the structured part of running the experiments. The idea of having a persistent database where you store all the experiments and all the variations, all the results that you did with the framework. And the key concepts are the universe itself, which is the database, the storage for everything else. The experiment, which is pretty much a pair of a domain and the population. And then the variation has the specific hyperparameters, the configuration of the experiment. And then each variation defines a specific instance of an experiment. And when you run it, you get a trace. The trace records the multiple generations of running that variation. So this is actually produced from a script which parses a Darwin database. So the blue things in the left, the blue boxes, are the experiments, and they point to the most recent variation. And each variation points to the previous variation, right? Because when you tweak something, you tweak an existing variation, right? It's based on the existing one, you modify something. And the database wants to capture this lineage. Like I had this experiment and I tweaked this parameter, but I tweaked it starting from this other variation, right? So you keep the whole thing. And then each one has multiple runs, like you can run the same variation multiple times. And I will explain there's a good reason to run it multiple times, but every time you run a variation, you get a trace. Does this one look familiar, this diagram? Does it look like something similar to, have you guys used Git at all for? So, it's not accidental, right? I took inspiration from version control, right? Because it kind of deals with the same thing, right? You have historical data, and so this would be the equivalent of branches, the experiment would be the equivalent of branches, and the variations would be maybe the rough equivalent of commits. You kind of have the whole history. And it's an abstraction that served well, but actually the gray dotted lines, they are actually branch operations. You can start from an experiment and branch into a different experiment. And anyway, this is an abstraction that served me well, but it has some limitations, so I'm actually not super happy with it. This is one of the things I'm trying to tweak a bit, but this is the current implementation. This is what it does. And I have, this is the schema. And as an implementation note here, the Darwin database is a SQLite database. It's really nice. SQLite is an embedded database engine. You compile it in your application, and it serves the database in one file. So one file is a database. You can copy it around. It's very convenient for this kind of applications. And it's a relational database. It's a SQL, more or less, database. And I run into some problems with the relational part, the schema being too strict. So the Darwin database it's a hybrid. It uses relational for the structure, for the graph that I showed you here. So everything here is like models a relational database. But the actual values, like the configuration values and all the other values, are JSON objects. So they are schemaless, So it's a combination between a document database and relational database. And that part worked really well. I'm really happy with that. So finally, like I was talking about domains, right? So this is some examples of the domains that are implemented in the framework right now. This is one of the early ones. Like it's a maze where he explores and he has to find. There's an agent here, and he has some form of vision and can navigate the maze and has to find the green things which are closed and avoid the red dots. This is a simple strategy game. There's a tic-tac-toe, which is of course like not a really hard problem, but it's a good sandbox for evaluating algorithms. And I recently added support for 2D physical simulation. And this is actually going towards what I'm interested in, which is robotics. I want to do more and more things based on physical simulation. And there are also some built-in automations. There's like the conventional neuroevolution, which only involves the weights in the neural network. And then the second one, NEAT, is one of the most popular and successful neuroevolution algorithms. It involves both the weights and the topology. It's a gold standard currently in basic neuroevolution. And I have a genetic programming operation as well, which is not technically a neuroevolution. It's a type of genetic programming. So, any questions before I go forward?
Yeah.
So, also part of the framework.
Right.
Yeah. Sorry.
So when you were talking about your database in there, I don't know if you, might be a little bit of a tangent, but you thought about, it looks like you could use that for co-evolving two different types of critters at the same time. And I just thought I'd throw that out to see if you thought about it, or it looks like you could do that, and if you had a related domain, or at least an overlapping domain, not as disjointed as you were showing, it looks like you'd be set up very nicely to co-evolve and do almost like a little ecosystem in there.
I'd love to hear more about that idea.
I just had it, so I'm making it up as I go.
Yeah, co-evolution is actually, it's a specific technique.
Yeah.
And I'd love to hear more about what you're doing.
But it looks like you're set up to do it,
Yeah.
or very close to it.
Okay, let's chat about that.
Okay.
So you showed the creatures and how the lower number, failed quickly, but how do you get those to evolve so that they don't fail quickly, even though they've been given a low starting point?
That's a very good question. Like how does evolutionary algorithms actually work? How do you get from worse to better? And the answer has to do with everything I talked about so far, with the selection and the genetic operators. So first of all, you select the candidates. In the traveling salesman problem, for example, I pick the top half, the better half of the population, so the ones that have some potential, and they are used as a parent. The idea is that you have maybe promising traits and you combine them a bit, you get better solutions. The second thing is how you define the genetic operation, how you do the crossover mutation. If you do, for example, in the traveling salesman problem, we have the rods. If we have a mutation operator which shuffles everything, that's a valid thing to mutate. But it's almost useless because that generates in random search. So random search is like when you really throw darts around, and maybe you find something that works, maybe you find something that doesn't. Evolutionary algorithms are a bit more refined than that. They pick up the things that work better and they move in the near vicinity of that thing, right? So it's not quite a gradient descent, but it uses some form of hill climbing. So if you think of the problem, like there are some places in the problem spaces that are better. Think of hills and valleys, right? So the hills are like where you want to get. That's the place where you want to get. If you have a solution that happens to be like close to a hill, that solution, there's an analogy in one of the books I really like, let's imagine like you drop people off with parachutes there, right? And they have walkie-talkies. The ones that are close to the hill, they will call everyone else and then they start like lost in space. So this is what makes evolutionary algorithms, gives them a bit of directed search towards better solutions. Like you pick up the best ones from a solution, they have a higher chance of reproducing, and then you combine the traits in a way that you have a good chance of combining two traits to get something even better.
But can you do that in the same object that uses surrounding characteristics to say, like a baby doesn't learn how to walk right away until they develop the muscles to do that, but they're developing the muscles, so you don't want them to fail at startup, you want them to keep evolving and growing. How do you keep your objects growing so that they don't fail?
That's a very good observation, and there is a lot of research in this space. You can have late bloomers, which are solutions which are not initially very good, but they have the potential of becoming better. The techniques become more specialized, so I'm not going to go into that, but if you're interested, let me know and we can chat about it after the talk. I think there's one more question.
So when you're creating a new generation from, say, the best half, you create the same size population as the original one, right?
Correct. That's not a, it doesn't have to be like that, but yes, like that's how it would.
So you'd have, it's not that you get half as many as you have parents or something like that.
Right.
Either the pairs have multiple offspring or they have multiple combinations in the pairing
Correct.
of the parents.
Yes, absolutely correct. And
Actually,
the,
yeah.
the example I gave is a simplistic one. Like a good selection doesn't work quite like that, like cutting things in half. But the idea is that it's like the population size is constant, every generation is constant. You just generate new solutions in every generation.
But do you kill off the parents, even if they may actually be better than their offspring? Or do you keep some of the parents and replace some of the parents with offspring?
Okay, so that's also a very good question. There's a special, I didn't talk about it here, there is a special genetic operator called elitism, where you keep a number of the really good solutions, you put them in the next generation. So they're not offsprings, but you keep exactly that. You keep some of the best parents, you keep them in the next generation. And it's a very important thing in evolutionary algorithms. Like you can have something like, like a 10% of the new population is the best, the best 10% of the previous one.
What's your equivalent of introns, right? What is your equivalent of useless code? Obviously in genetic programming there's useless code fragments. Is there an intron area in evolutionary algorithms?
Okay,
Neuroevolution.
That's a very it gets a lot into the the details of the code.
Yeah.
Since we're talking about artificial neural networks, introns are kind of implicit in the network. Is the nodes that don't really contribute to the output. Right? So if you have, for example, a weight of 0, like whatever neuron is connected to that has that weight connected to its output is not going to influence the solution. Right? So that's kind of they're like implicit neurons in the neural network. And some of the other so these are actually genotypes, like 2 types of genotypes. This is from NEAT, the one that can generate topologies as well, the weights, and that's from the Cartesian genetic programming. And this one can generate like new nodes, and if they're not connected, like the output is not connected to anything, that's technically an intron.
I mean, do they generally get removed from the system just because of just the nature of the design, or do you keep them as you go forward in evolution? So obviously, in an evolutionary standpoint, there are lots of debates between keeping stuff which is useless and moving it forward, or the computer science world where you just want to get rid of useless stuff because that's.
You know better than I do. Introns are positively beneficial to evolution.
That's right.
There's no explicit thing in these algorithms that gets rid of them. But there's one type of pruning, right? Like you can do if you find a good solution, for example here, like with the Cartesian genetic programming. Right. This is actually a simplified version because there are more nodes that are not shown. So I prune it when I have the final solution. If the solution is a program with neural network, I can do post-processing when I productize the solution and trim it up. Yeah, so I don't spend too much time on this because it's a somewhat obscure or subtle thing in the neural networks. Again, these are also from the framework is a way of visualizing the genotypes from 2 different kind of populations. And this is a neural network. Like this is actually how it looks, and this is a recurrent connection. And yeah, the numbers here, like they have some specific meaning to me, but they're not the weights, by the way. Any other questions? So another thing that the framework does is we are not manual plotting things. So top left, plotting figures over, like these are generations over time, so we can see how things improve. And there are some interesting things here. You can see like some like big stiff parts or like the bones, and then flattens out a bit. But this is plotting, the best candidate, the best individual in the generation, the median and the worst, and moving the average there, the big blue line. The next one actually compares two different algorithms. This one is a batch one, so it's the same algorithm but run multiple times. Evolutionary algorithms are stochastic algorithms. So you don't get exactly the same results every single time. But you kind of want to know that, they're not completely randomized. It's a good way to make sure that they are somewhat predictable. And the final thing is the distribution of thinness in a population. It's a technique I use a technique used in 2D animation, onion filling, so different colors kind of like show you like the previous generations, the old generations. Just to give you an idea of the things that you can do after you run an experiment. And this is the thing that puts everything together. It's an IDE for running evolutionary experiments. It's called, I call it Darwin Studio. And if we have time, maybe we'll do a live demo. It's intentionally made. It's inspired from an IDE, like program an IDE. You can run the experiment. You can even interact with some of the domains. So. Any questions before I move to the final part of the talk, which is more C++ stuff? So I collected a few notes here about the implementation. In no particular order. First, I want to pick one example of one abstraction that worked well in the framework. And it's something that also fills a goal in the current language. I needed reflection. So populations and domains, they have these parameters, and I want to be able to tweak them not in the code, not carefully in the code, but expose them in the UI and serialize and deserialize them. So I needed basic structure reflection. And I also wanted to have really fast, low overhead accessing of the values. So when I actually run the algorithm and uses the configuration values, I want to make it as efficient as possible. So the property set is exactly that. It's a reflected structure that has some interesting characteristics which were intentionally designed to fit these requirements. So the most important thing is accessing fields in this reflected structure is as cheap as accessing plain old fields. And the second thing is that it has built-in support for serialization from JSON, and it's a very forgiving serialization in that it has a form of loose versioning. If you add a simple field, for example, to your domain, you don't want to have all the experiments that you already run. You don't want them to stop loading simply because you added a field to a domain or you remove one. So it has an interesting thing that worked really well in terms of how we load. So when you load something from JSON, if there is a field in the JSON object that's not in the real property set, then that field is going to be ignored. And if the property set has a field which is not present in the JSON object, it's going to use the default value. And it also has has built-in UI components. Like in the right here, this is how it looks like. The property set, you know, it's almost no code to set it up like that. That UI component just passes the property set and can display the whole thing and you can edit the values as well. So this is a piece of code. This is how the property set looks. The top part is how you define it. And you have to derive from the property set type, and also there is the property macro. And it's kind of self-explanatory. It's like the name of the field, the type, the default value, and there is also a string which is used both for reflection and also it's used both for serialization, also used in the UI. And then when you use the fields, they're exactly as plain structured fields because they're actually plain structured fields that get generated. And finally, like if you want to reflect it, this is how it's reflected. You can get a config object of a property set object as these properties accessor that is going to give you a list of properties, and each property you can access the name and the value. Should I move forward? All right. So one of the things here with having a project where you can do whatever you want is I used the latest C++ that's available. In most professional settings, you usually have to deal with constraints, and most of the constraints when you're dealing with C++ is usually limiting the features in the language and or the version of the language. I used to work for Google Chrome, and was really painful to move from C++ 11 to C++ 14. The style itself it documents what you can use and what you shouldn't be using. So in this case I had complete freedom, so I intentionally wanted to use whatever I can. I wanted to see like what are the consequences of using the latest things. Obviously, I only used things that are available, are supported by the toolchain, so the platforms that I was targeting. And Darwin is a cross-platform project. I'm using it and building it on Linux, Windows, and Mac OS, and using the GCC client and MSVC. So, multiple toolchains and multiple platforms. But it didn't limit the availability of the features, so I was able to target C++ 17 easily. So I think like some of the restrictions are perhaps too harsh in some of these settings, and I hope to see a bit more flexibility using the languages it's designed. And I have some examples here. Things that I use because I actually had the use for them, not just because I wanted to try them. Is there anything else? I have like the source code. If anybody's interested, I can point some things in the code, or we can do that later. Okay, so no takers then. I'll move on, and if anybody's curious.
So you're using std optional. That's for visitor pattern somewhere.
Sorry.
So you're using std optional. Is that for returning a value in error code?
Yes, so std optional was super useful when dealing with the database. Right, database has nullable fields, and how do you represent that when it's a nullable? It's a nullable, not a pointer, but it can be an integer or floating point value or a string. std optional is a perfect match for database interfaces. And also the structured binding declaration is also super useful. You have also for databases when you return something, a row from the database, you can easily unpack it into multiple values. It's a beautiful, the codes are a lot of beauty. It's a great feature.
Did you see something that you thought was missing out of the standard for this particular project?
Yeah. I mean, I had to build a reflection, right? Like I had to build that.
Just wait for 23.
Yeah.
What's that?
Just wait for 23.
Okay. Yeah.
That's when the
Maybe the other languages are going to come up in
reflections was in proposal for 20, but then got pushed out, so it's 23.
And it's a different kind of reflection, the one that's proposed in the language. It's not exactly what I think here, but But yeah, I mean, I'm sure that C++ is going to continue to evolve. But today you can actually use, there's a lot of good things that you can use. And they're not, they're not complicated features. They're not like really flashy complicated. They're not like modules or code keys. They're small but very useful features. Okay, so error handling. So this is my favorite slide. On the implementation side. I have other favorite slides on the Neuroevolution side. I know some people feel strongly about things related to error handling. I've been programming for a while, and I'm starting to form some strong opinions myself. And in Darwin, I started everything from scratch, and I applied one of the philosophies I believe in consistently throughout the whole project. And so far, it's been very successful. And the approach is this: be very explicit about the contracts, assert everything, which I'm sure everybody here does. And really assert everything that's wrong. So first of all, this is the antithesis to defensive programming. So no things like this: if pointer equals null. No. If you want to check something, if that pointer really shouldn't be null, just assert that is not null. The second twist to this is, once you assert everything, fail fast. If an assertion fails, don't do anything, just crash hard. Produce a crash number if you want. And the kicker to the whole thing is that I have assertions in all build papers. And we've been taught for more than 30 years that you have a debug build with the search enabled, and then you take out the seat belt and you ship the release bug. And I found that there are very few cases where that thing makes sense. Obviously, there's an overhead to shipping with the search enabled, but there's a lot of value. So there are some places where you can make a case that you don't really want to have a search enabled. But I would claim that for the majority of the code, you want to ship with the search enabled. And there are some implications to this. First of all, you want to make sure that the debug builds are functional, so your asserts are actually good. I don't know about you guys, but I work on products where the debug build was unusable because it has so many asserts that fire. Like I worked on OSs that couldn't boot because you get asserts like in the first 5 seconds of the boot process, or the debug build was too slow. So once you have the assertions universal and uniform, like you're kind of forced to treat everything seriously. Like the asserts are there. There's no excuse that an assertion is correct. The assertion is plenty of things. But there is another interesting consequence here. If you apply this practice, then the question about what you do with error handling becomes very difficult because you find out that there's very little that's left in terms of error handling. A lot of the stuff is simply contracts that you check. There's very few things that are really error handling that have to be handled with contract. And in these cases, I think it's a reasonable thing to use C++ exceptions, which is another thing that a lot of people have opinions, pros and cons. But for things that have to be handled now locally, I don't know anything that's better than C++ exceptions. Go ahead.
So since you're at the forefront of the language, in 20, I think we're getting contracts and concepts.
Right.
So how does this change in that world?
I'm not very familiar with the latest proposal for contracts.
No one is.
Let's take a look. But I from what I remember, it's very close to, it's along the same lines.
Yeah. So would you change everything there to move to contracts, or how would you handle that?
I would really have to see what the final language looks like.
Aren't you worried about performance, or is that something that evolutionary, whatever takes its time.
Yeah, yeah. I mean, I'm very concerned about performance. I mean, this is one of the reasons I'm implementing the whole thing in C++, the core framework in C++. There are parts in Python, but the core is in C++ because, yes, I want things to run fast. I don't want to wait, days when I can, do things in hours and minutes. But if you're implying that, having the checks there slow down things too much, I will tell you that the slowdown is not as much as you. So first of all, most of the code is spread in class, and very few pieces of code that really fast. Everything else, just doesn't really matter. And there's another interesting thing, like if you have these asserts, this type of aggressively enforcing contracts, you are left with very little error handling, and you find out that actually the code size can be smaller. Because instead of having like very sophisticated things where you pass values around just to be ignored 10 levels higher, you actually have a much thinner code. So yes, I do care about performance. I don't think these two are exclusive. If you have a super optimized code that has to be as fast as possible, and I have some things where I handcrafted with increases and stuff, yes, in that places I'll be mindful of the kind of checks I have. But for most part, I think the value overweights the costs, which are not high.
Yeah, just on that note, one other trick I've used where I didn't actually have a search turned on in production code, but what I did was trust boundaries. So at layers, I would have the equivalent of an assert, and then it would be off under that, and that really mitigates the cost of using it.
If you can have the discipline to define the boundaries and enforce that, it sounds like a great
It's kind of a halfway step to what you're doing.
So you can do a lot of conditional checks to see, does this parameter, is it null? If it's null, don't use it.
Yes, and it can be useful sometimes to have that kind of training on and off. But then you have an extra check in the code, right?
Yeah.
So you're talking about performance, first you have to check if the knob is on, and then you have the real check, right? So.
Well, asserts basically cause your program to fail, and it's instant. So.
Yes, but I mean, you still have the code generation, right? You still have the code there that has to check for that condition. Even if it's disabled, if the knob is disabled, you still have to have that check in branch, conditional branching. So yes, I mean, it makes sense if you have a very expensive check, for example, that does some complex validation of the data structure. Maybe you can use something like that.
You were talking earlier about the peaks, solving for the peak and trying to climb and getting better and better scores. What about when you have the multi-peak with a deep valley between them? So by the time you're always optimizing for the top half, you're not getting any of the negative feedback of the mutations, on top of mutations that are getting worse and worse, that may find the valley and climb up the next peak.
That's a great question. Being trapped in a local optima, which is what you're describing, is a hard problem in machine learning and neuroevolution and artificial intelligence. With the evolutionary algorithms, you can solve it. There are some ways you can mitigate it. You can have, for example, population diversity. Instead of focusing everything in one peak, you can keep you can keep track and use the metric of diversity, making sure you're covering a large space somehow, right?
You're hoping your initial population lands on both peaks.
So you can have the initial population, or you can have more sophistication, right? If you find everything converging on one spot, you can intentionally see things around. The algorithm that I described here, one of the algorithms that's implemented in the framework, has the concept of species. So it does microevolution within species, and the species they stay separate from each other. So if one species one peak and one is not a peak, one is not going to take over the other one. It's a hard problem, but yes, I mean there are ways of mitigating that.
Well, nature mitigates that by actually separating the populations so they can't interbreed. Then they evolve independently, and then they collide again.
Which is the idea of species, right? That's why speciation is one of the things, the inspiration for this part.
I mean, that's what species are, is they're finding different local optima.
Let's see what I have here. So I'm very impressed by for I'll be surprised that very controversial here, like shipping with the certs.
Speciation.
So a quick, just a quick note on random numbers. We are dealing with stochastic algorithms, so randomness is really important. And C++ 11 introduced the random utilities, and they have a very nice interface. They have, I don't know if you use them. They have, it's a world apart, world ahead of the old rand function, which just return random value. So we have like the concept of random number generators, engines, and distributions. But not everything is so great in the rand world. The standard implementation has a number of problems. And there are two classes of problems. One of them is the entropy, the seeding. The interfaces and the current implementations are really poor at generating the right entropy. And then the second thing is performance. The performance is not as great as it could be. I'm not an expert in this field. I can point people to some links if you're curious about details. And there is actually a really good blog that explains the problems of the entropy, the seeding here. So the takeaway here is that it's great that we have the random utilities in the standard library, but they are not perfect. Don't assume that they are the ultimate thing in random number generators. If random numbers are really important to you, maybe it's time to do a bit of shopping around for alternatives, even with the random in the standard library. So I have a slide here on the third-party dependencies. I imagine everybody's a bit tired by now, so I can skip this part here. So, would you guys prefer, like, some notes on third-party libraries or a quick live demo? Who would like a live demo? I'm curious, like. All right, it's a bit more than half, so let's do the live demo.
Bring out those demo.
So that's the last thing I have here, and the rest is like some links. This is Qt Creator, which is, by the way, an excellent cross-platform from C++ IDE. It's really great. I love Visual Studio as well. I used to work for Visual Studio, but I really like Qt Creator. So I apologize, like the fonts are small here, so you won't be able to read everything. This is Darwin Studio, the evolutionary algorithms IDE that I described. And I'm going to start a brand new experiment. And I want to walk you through because I know you cannot read it. So here is like the first thing where you can pick the domain and the population. So I'm going to pick the unicycle domain. And you'll see what it does. And this is the population. This is the type of algorithm that we are using. And we'll leave the population size 5,000. So this is the, on a powerful computer it can go a lot higher, but only, maybe 5,000 here. You can name the experiment. You can say live demo. And now what we have here on the left, and again you won't be able to read, is like all the tweaks, the hyperparameters. For example, in the domain, I can change the gravity. It's 9.8. I can change the beta 1. The pore length and wheel radius and all these things. In the population, I can change the activation function and many other things. So I'm not going to click that stuff. I'm just going to let it run right now. And when I run it, I can set a termination criteria here and a few other things, but I'll keep the defaults. So this is just the log window. The top two things here are, the top one is the time it takes for each generation. The one that's really interesting is this one here. This is the thinness. So I have the blue line is the best candidate in that generation. The red is the worst, and green is the median. And on the right here, it's also kind of the same values in the table, and you see the progress of the generation. So we got the generation 8 right now. So I can pause the evolution right now. And another nice thing here is, since it's a visual thing, I can actually I can interact with all of the solutions. So I can pick up which generation I want to use, and I'm going to use the champion, the best solution in that generation. So let's see what the generation does. Generation P. So unicycle is the unicycle problem is that it looks exactly like this. There's a wheel in the pole here, and the input to the algorithm is the angle of the pole, and what the brain, the artificial neural network, has to decide is how much torque it applies to the wheel, one direction or another. So the first thing it has to do, it has to balance the pole, which it already does pretty well. And the second thing here is there is a small arrow, and it's supposed to get as close as possible to that location. So I can actually move it and right here. And this one is doing actually pretty well. Like I can move this stuff, and it's not too bad. So let's see if I go all the way here. Oh, cool. You know, if we let it run a lot more, it's going to refine a lot. This is already like, it is doing a decent job, but if you really run for a few hundred generations, it becomes a lot more precise in how it balances and how it, you know, targets the destination, the target location. You guys find this interesting? Sure. We actually one more domain. All right. Let's do one more. I'm gonna abandon this one here if I can find the mouse cursor. So I'm gonna say let's do another experiment. I'm gonna start with that one. This one is the harvester, is the maze one. I'll show you, and let's use like the fit for the neural network. Say population 5,000, and let's see here, like I can change, for example, the vision resolution. So right now vision resolution is very low, like 3. It has like 3 rays that it uses as input. You can set it, you know, a lot more. Let's see, this is actually just sure. Let's see this one. So let's run it. Kind of the same thing, like, you know, we're going to go like, and you can see, you know, this is a very modest laptop. We can still go through generations pretty fast. I mean, that's one of the nice things about C++. You know, I have multiple threads here, and you know, I have a bit of ADX2 optimization that's handcrafted, and overall, it, you know, performs pretty well. And I'm going to set up curiosity here. But at least I managed to tag all the threads. You know, in the winter I can turn it on and I can keep the room. All right, so this one is also making some good progress here. So let's see what it does so far. So, I'm going to try to make that in a bit deeper. And close these. Can you see right now? Be better? So let's see what it does, like if I let it go on. So the little view there right now is a bit chaotic, but you know, it ate some red stuff, not particularly smart. It's not very good at avoiding the poison cells. Okay, so, you know, we let it run here. And I'm going to let it run here. I'm going to take any more if you guys have any other questions.
In this example, it's not very extreme, but in the previous example, you could see that the median had a hard time to kind of approach the maximum, and the maximum didn't even move really much. It stayed kind of constant. So why does this happen?
That's an interesting question, right? So remember, I had one of the slides. I can go back here. Let's see. the fitness distribution, right? Like, so median kind of tells you like how the distribution is. So one thing that can happen is that if you get stuck in local optima, which somebody was asking, then you don't have a lot of diversity in the population. And you're going to see the median and the best, stay close to each other. That's not exactly a great thing. That means like you don't have anything, to build upon. If the median stays really low, that means like the distribution is like really skewed towards like worse, really bad solutions, and that can happen if you have like really poor genetic operators that don't allow solutions to evolve. It's a bit of, I would say it's a bit of black magic, like learning how to interpret this, which is why it's so important to have the right policy. I learned a lot about data science and statistics working on this project because questions like that require a bit of fundamental knowledge around statistics and data science. And yes, I mean the most important thing is to have the tools. Looking at the distributions and how things evolve, you can build some hypotheses and then you go back to the code, or you can do things and you can validate the hypothesis, which is exactly why the framework is important. Like you have these questions, you wonder why something works or it doesn't work, and then you try something, right? And it goes back to structured experimentation. You do some things, you start with a hypothesis or some question, you do some different variations, and you may or may not have your answer, but at least like the path you go. This is a pretty hard problem. Like I'm not sure if this is gonna get a lot better, but I will let it run for another minute here. I'm going to show you one more video, and I'm going to wrap it up with that. It's a classic video, and I have a feeling that some of you may have already seen it. It's called Virtual Creatures, Carl Sims. This is something from, I think, the 90s. It's not exactly new, but it's really beautiful. It's a virtual environment that involves creatures and involves both the morphology, like arms, legs, whatever they have, and also the controllers, like how they move. And it's a collection of these things that involve like really interesting things. It's low resolution because it's from the 90s. But it's one of the things that I remember seeing this stuff and I was like, oh, this is really cool. Like, that you can actually build things that would surprise you, like, because these are not designed, they're not hard coded. Like nobody can design like these styles or these things. And I found that really, really fascinating. The kind of things that emerge, like the fact that you have unexpected things like this kind of movement, right? And so with this, I'm going to stop here, unless you guys have any other questions. Yes.
How often do these unexpected surprises happen when you actually experiment with the Darwin Studio?
Quite a lot.
Okay.
Quite a lot, which is one of the interesting things. And I think this is one of the really, it's a pro and a con, right? I mean, if you're building something where you really want to be able to interpret and control the results, this could be a liability, but it's also one of the interesting things about the algorithm. All right, thanks everyone.
Thank you.